Have you ever really stopped to look at a car bumper? I mean, really looked. Especially those old, shiny, chrome-finished ones.
Ah, yes. That perfect mirror finish. It really catches the eye, doesn't it?
It does. But then you tap it, and you realize, wait a minute, this sounds like plastic. Or maybe some kind of cheap metal underneath. How do they get that perfect layer of chrome
Hmm.
to just stick?
Right. It's not like they use some kind of super glue.
Exactly. And that's our starting point today. Welcome back to the Deep Dive. Today we're jumping into Unit 2, Electrochemistry, and we're tackling a topic that honestly gives a lot of students a bit of a headache: electrolytic cells and electrolysis.
It's a big one. And it's really the other side of the coin from what we've been discussing. We've talked about galvanic cells, batteries, where a chemical reaction just gives you electricity
And spontaneously.
spontaneously. But
Yeah.
today we flipped the script completely.
We're flipping it. So why should we care about this? What's the mission today?
Well, the mission is to understand how the modern world is built. I mean, think about it. The aluminum in your phone, the pure copper in the wires,
The chrome bumper.
the chrome bumper, exactly. None of that stuff exists in nature in its pure form. Nature prefers, oxides and ores, chaos, really. To get these pure structured materials, we have to fight nature.
Fight nature. I like the sound of that.
We do, and electrolytic cells are our weapon. We use electricity to force chemical changes that would never ever happen on their own.
So if galvanic cells are about chemistry, giving us power, this is about us using power to boss the chemistry around.
Precisely. It's brute force, but with atomic precision.
Okay, I love that. So let's start at level 0. I'm a student. I'm feeling a bit lost.
Yeah.
Give me the simplest possible picture.
Okay. Picture a ball at the bottom of a hill.
Right. Got it. A ball on the grass.
Now, a galvanic cell, a battery, is like that ball starting at the top of the hill. It just rolls down on its own.
Spontaneous. Easy. It releases energy.
Exactly. But an electrolytic cell, that's you at the bottom of the hill having to push that ball all the way up.
It does not want to go. It takes work.
A lot of work, constant effort. You have to apply force, in our case it's external electricity, to make this non-spontaneous reaction happen.
And what happens if I, stop pushing halfway up?
It rolls right back down. The moment you cut the power, the electrolysis just stops, dead.
That's a really clear distinction.
Okay.
So let's zoom in.
Alright.
What's actually happening to the particles, to the electrons?
So imagine you've got two metal rods, our electrodes, in a solution. When you connect a battery, you create an electron pump.
A pump.
Yes, the battery starts pulling electrons from one electrode and force-feeding them to the other one.
Okay, so one is being starved of electrons and the other one's getting stuffed.
That's a great way to put it. The one connected to the negative terminal gets super rich in electrons. It becomes negative. We call this the cathode.
Right, the cathode, it's the electron dumping ground.
And if you're a positive ion in the solution, say a copper ion, you see this super negative place packed with electrons.
You're going straight there. Opposites attract.
You rush over, grab some electrons, and you undergo reduction.
Reduction is gain. Redschi. Got it.
Meanwhile, on the other side, at the anode, the battery is ripping electrons away. So the anode becomes positive. It's desperate for electrons, so it starts pulling them from anything nearby,
Causing oxidation.
causing oxidation. So the battery creates an electron famine on one side and a feast on the other.
Okay, stop. I can feel a major confusion point coming. A board exam danger zone.
Ah, yes, you're right. This is probably the biggest one in the entire unit.
We just talked about cathode, anode, positive, and negative.
Yeah.
And it's not what I remember.
It's not, because in galvanic cells, what did we learn? We learned that anode is negative.
Lone. Left oxidation, anode negative.
Yes. Well, in an electrolytic cell, you have to flip the signs.
You're kidding me. Say that again slowly.
In electrolysis, the anode is positive plus, and the cathode is negative.
Oh, wow. Okay, why? Why would they do that to us?
I promise it's not just to be difficult. It's about who's in charge. In a battery, the chemical reaction is the boss. It produces electrons at the anode, making it negative.
Right, the anode creates the negative charge.
But here, the external battery is the boss. It pumps electrons into the cathode, making it negative, and it sucks them out of the anode, making it positive. The signs are signed by the power source.
That's the key. It's not about what the reaction wants, it's about what the battery's doing to it.
Exactly. So for your exam prep, electrolytic anode is positive. Just drill that into your head.
Okay, I'm writing that down.
Okay.
Now, to help this all sink in, let's try another analogy. The ball on the hill was great, but what about a mechanism?
Think of a simple water pump.
Okay.
Water flows down on its own, right? That's spontaneous, but it will never flow uphill to a rooftop tank by itself.
Nope, not going to happen.
So you install a pump, you plug it in, the electricity does work, forcing the water against gravity. Unplug the pump.
And the flow stops instantly.
That's electrolysis, 100% dependent on that external push.
I have another one. For anyone who drives, putting a car in reverse on a slope.
Ooh, I like that one. Go on.
So the car is facing downhill. It wants to roll forward. That's the natural tendency.
Right.
But you put it in reverse. You hit the gas. You're forcing the engine to work against gravity, to go in the direction it doesn't want to go.
That is a perfect analogy. You are burning expensive fuel or electricity to fight the natural role of the chemical system.
Yeah, why do we do it? Why go to all this trouble?
Because the results are incredibly valuable. Most metals in nature, like aluminum, they love being bonded to oxygen. They're happy as rocks.
They're comfortable. They want to be a shiny phone case.
Not at all. To get pure aluminum, you have to force that divorce. You have to rip it away from the oxygen it loves, and that takes a huge amount of energy.
So we're basically electrocuting the ore until it gives up the metal.
In a way, yes. And we have to thank the great Michael Faraday for figuring this all out. He showed how electricity could drive chemistry.
Okay, let's do our mental movie. I want everyone listening to close your eyes, if you can safely do so. Let's build the scene.
All right, we have a glass beaker. And inside is a beautiful deep blue liquid. That's a copper sulfate solution.
Okay, I can see it. Deep blue.
Dipping into that blue solution are 2 copper rods. Our electrodes, they're wired up to a battery.
The scene is set. Nothing's happening yet.
Flip the switch. Action.
What happens?
Zoom in on the cathode, the negative one. The positively charged copper ions, the C2 plus ions, they feel that negative charge. It's like a magnet.
So they're all rushing towards it.
They swarm it, they hit the surface, grab 2 electrons each, and poof, they turn into solid, shiny, metallic copper atoms.
So the rod itself,
Yeah.
what does it look like?
It starts getting fatter. A fresh, bright layer of copper starts plating onto it. It gets thicker and thicker.
The cathode gets fat.
Oh,
Okay.
okay.
Now what about the other one, the anode, the positive one?
Over there, it's a horror story. The anode is desperate for electrons. It starts ripping them from its own copper atoms.
It's eating itself.
It is. The solid copper atoms lose their electrons and dissolve into the solution as new Ce2 plus ions. The rod gets thinner. It gets pitted and starts to shrink.
So the movie is the fat cathode and the thin anode.
Perfect title.
And what happens to the blue color of the solution?
It stays exactly the same.
Wait, how? If copper is coming out of the solution to plate the cathode, shouldn't the blue color fade?
It should, but for every copper ion that lands on the cathode, a new one is created as the anode dissolves. The concentration stays constant.
That's brilliant. It's a perfect cycle.
And the most important part, the director, yells cut and pulls the plug.
Everything stops.
Instantly. The movie is over.
Wow, okay. Let's take that fat cathode idea and go back to my spoon, or the bumper. How does electroplating work?
It's the exact same movie, just with different actors. You want a silver plate, a cheap steel spoon.
Yes, I want to make it fancy.
You have to make that spoon the cathode,
The cathode. Why?
because the cathode is where things get plated. It's the fat electrode. You want the silver to stick at the spoon.
Oh, right. If I made it the anode, my spoon would dissolve.
It would vanish. Total disaster. So, spoon is the cathode. The anode is a bar of pure silver. You turn on the power, the silver bar dissolves, and those silver ions swim over and plate your spoon.
And my cheap spoon looks amazing.
This is how it's done. Gold plating, chrome plating. It's all just using the fat cathode principle.
Okay, here's a smart student question.
Yeah.
If I want this to go faster in my factory, can't I just crank up the voltage? More power?
Ah, yes. The more power fallacy. It sounds logical, doesn't it?
It does. Let's get this done in 2 minutes, not 20.
But if you apply way too much voltage, you start triggering side reactions. See, the solution is mostly water.
Right.
If the voltage is too high, the electricity gets lazy. It stops bothering with the metal ions and just starts splitting the water molecules apart.
You mean making hydrogen and oxygen?
Exactly. You'll start seeing bubbles of hydrogen gas at your cathode and oxygen at your anode.
And bubbles are bad for a smooth finish, I'm guessing.
Terrible. You get a pitted, spongy, brittle coating. It's ruined. Plus, you're just wasting electricity making gas.
So it's about precision, not just raw power.
Absolutely. It is a
Yeah.
very delicate balancing act.
Fascinating. Okay, let's shift gears for the students listening. Time for our exam-safe clarity lines. The key takeaways.
Let's do it. These are the things you must have clear in your head.
Number 1, the signs.
The big one. In an electrolytic cell, The anode is positive. The cathode is negative. Just say it over and over. Do not mix it up with a battery.
Got it. Number 2, the processes.
Remember these two little rhymes, red cat and ox.
Red cat and an ox.
Reduction at the cathode, red cat,
Yeah.
and oxidation at the anode, and an ox. And this rule is universal. It's true for batteries. It's true for electrolytic cells, always.
Okay, that's a relief. Some things stay the same. Point 3, Faraday. The math part.
Just know the relationship is direct. More current or more time means more metal gets deposited. It's a simple, linear relationship. Double the time, yet double the thickness.
Predictable. Good. And finally, number 4.
Power dependency. This process is non-spontaneous. The moment you remove the external power, it stops. It needs that constant push.
Fantastic. I feel like we've really built this concept up from the ground. Let's do a super quick summary.
Okay, core idea. We're using electricity to push a reaction uphill.
Our mental movie. The blue beaker, where the cathode gets fat and shiny while the anode gets thin and disappears.
Our application. To plate a spoon with silver, you make that spoon the cathode.
And the most critical exam point of all.
In an electrolytic cell, the anode is positive.
Perfect. If you can remember those points, you're in great shape for this topic.
Absolutely.
I want to leave everyone with one final thought. We talked about this as fighting nature, right? Purifying metals.
Yes, fighting against entropy.
Think about the sheer amount of energy that takes. We're taking messy, chaotic ores and forcing them into a state of pure order. Pure aluminum, pure copper.
It's true. Before this process was industrialized, aluminum was actually more valuable than gold.
Exactly. So every time you hold a soda can or see that shiny bumper, what you're really holding is frozen energy. All the electricity it took to create that order is locked inside it. The moment the power cuts at the factory, the process stops.
That's a great way to think about it. It really puts the material world into perspective.
So next time you see that question on your exam, picture that movie, remember the fat cathode, and know that you're in control of the whole process.
Good luck with your studies. Keep those concepts clear.
Thanks for listening, and we'll see you in the next deep dive.